Okay, this is Algebra 1, Lesson 11.1, and it is expressing roots, expressing roots. All right, so let's all start off with some terminology here. So if you look to the right, right over here, we're looking at a radical here, and it's important that we know what the name of each part of the radical is. First off, the symbol itself. A lot of people want to call it a square root, but a square root is just one kind of a radical. So the blue symbol here is really the radical sign. It's the radical sign. Then you have the part of which you are taking the root. It's underneath the radical sign, and that's called the radicand. Radicand. C-A-N-D. There's a D on the end of that word. May not be able to hear that with my enunciation. All right, radicand. So you got the radical sign, you got the radicand, and then you have oftentimes something in the crevice, and that is called the index. The index. So those are three parts of radicals. You've got the radical sign, you've got the radicand, and you've got the index. Let's talk about each of them right now. So again, the radical sign here is number one, and it simply indicates the operation of a root. And if you remember, when we talk about mathematical operations, we're talking about things like addition, subtraction, multiplication, division, absolute value, things like that, right? So the radical sign tells you, hey, you need to take the root. You need to take the root. Secondly, the radicand is everything under the radical sign, and here's the key. It's what you take the root of. You're taking the root of the radicand. Taking the root of the radicand. And then third, the index. And the index is really important. It indicates what kind of root it is. It can be a square root, a cube root, a fourth root, an eighth root, a hundredth root, all kinds of possibilities. And the index tells you what kind of root it is. Don't forget this. If no index is shown, in other words, you just have the symbol here. Let me draw it for you, right? You just got the symbol. You've got no index. There's nothing indicated in this crevice. Then what is the value of the index? Well, we all know when we look at this, we say this is a symbol for a square root. And what is the index of a square root? It is 2. So when no index is shown, the index is actually 2. And of course, it's a square root. No index is shown, the index is 2. And it's a square root. All right, some terminology. It's important that you know that because as we reference some of these things, you need to understand what they are so it makes sense to you. All right, types of root. Remember, the type of root is determined by the index. The type of root is determined by the index. Square root, cube root, fourth root, etc. So again, one more time here, an index of 2 implies a square root. Will that index be shown? No. Do they expect you to know that it's a 2? Yes. And what exactly is a square root? Well, simply this. Here's the operation of square root. What number times itself 2 times equals the radicand? Now, how in the world did we come up with the number 2? Where possibly did we get the idea that a number times itself 2 times? I'm sure there's nothing at all anywhere that would give us any indication that it's 2 times. Well, of course, that's what the index is all about. Right? The index tells you what kind of root. So when the index is 2, it's what number times itself 2 times equals the radicand. All right? The index is the key. And so square roots, what number times itself 2 times equals the radicand. All right, so here's an example. We're over here on the left. We've got the square root of 9, right? So square root of 9, we all know the answer, right? Everybody knows the answer is 3. I'll stick that there right now because you know the answer is 3. But what is a square root really saying? What's the square root of 9 here? So in green, what number times itself? Of course, the square root, right? So 2 times equals, well, let's not use the word radicand. Let's put the radicand. What is the radicand? It's a 9. So that's the question. What number times itself 2 times equals a 9? And of course the answer is 3. Why? Because 3 times 3 equals 9, right? What number times itself? A 3 times itself 2 times equals the radicand. All right, so number 2. Same kind of concept. We've got the square root of 49. So again, you look at it, you say, oh, square root. That's an index of 2. So what number times itself 2 times equals, and what's our radicand in this case? 49. And of course, this is one that we all should know already anyhow, and we all know the answer is 7. And why is the answer 7? Because 7 times 7 equals that radicand of 49. That's the aspect. These are not hard, and they're not meant to be hard. All right, number 3. You be careful in something like this. In this, we've got a lead negative out in front. Now remember, this is exactly the same as a negative 1 times the square root of 25. We just don't need the 1 there, just like we don't need the 2 for the index. If there's no index, you know it's a 2. We don't need the 1 there because a negative square root of 25 is exactly the same as a negative 1 times square root of 25. But that's what we have. And so in this situation, our solution is going to be, I'm going to use my red here, you're really going to end up with a negative 1 times, and when you take the square root of 25, you get 5. And so final answer is a negative 5, right? Just needed to apply that negative that's out in front. Number 4, we've talked about this in the past, and I don't know if you remember, but square roots undo squares. So if you look right here, you've got the square root symbol, and if you look right here, you have the radicand squared. So remember, what is a square root? What number times itself 2 times equals the radicand? What is the radicand? Watch now, listen. The radicand is the number 17 times itself 2 times. So what is the solution? The base, 17, right? What number times itself 2 times is 17 times 17? 17. All right. And look, this is the case whenever the exponent of the radicand matches the index. That's a key concept. Whenever the exponent of the radicand matches the index, then the root is the base. The base, remember 17 is the base, the red 2 is the exponent. Okay? So just quickly, if you had something like this, the square root of z squared, well then the square root of z squared is z, right? The base. What times itself 2 times is a z times z? How about a z? All right, let me get rid of my shade so I can put my screen a little higher. All right, so let's look at B here. So what if you had an index of 3? All right, not a problem. If the index is 3, now we have a cube root, right? Index of 3 would be a cube root. And what should you think of when you come across a cube root? Well, this is what should be in your brain. What number times itself 3 times equals the radicand? Again, the index tells you how to perform the operation of taking the root. Cube root, what number times itself 3 times? All right, so if we look at the first example here, we've got the cube root of 8, right here, cube root of 8. So what's the question? What number times itself 3 times equals that radicand of 8, right? And most people know that the cube root of 8 is 2. Why is the cube root of 8 2? Because again, over here to the right, 2 times 2 times 2 equals that radicand of 8. So what number times itself 3 times is an 8? The number 2. The number 2 is the answer. We've taken the cube root of 8. We figured out the operation of what number times itself 3 times equals that radicand of 8. And that's what we're doing here. So again, here's our example. Like we had on number 4, notice that the exponent matches the index. Whenever the exponent matches the index, the root is the base. The answer is x. Because again, what do we have here? Let's go back. What number times itself 3 times equals the x cubed? Well, the answer is x, because look, x times x times x is x cubed. That's what we're talking about. Those are the aspects here. All right, let's go to the next page of your notes. So a couple more examples. All right, so here we've got that negative out in front again, so we know we're going to have a negative. And then we're going to take the root. What number times itself 3 times is a 27? Most people know that the answer to that is a 3, because 3 times 3 is 9, times 3 is 27. So in that example, we have a negative 3. Number 4, we've got a compound situation. You got two things going on. You've got the 5, and then you're going to have a negative, the cube root of 1,000. Well, like and when you memorize the order of operations, hopefully you still remember this. Evaluate all exponents, multiplication, division, left to right, addition and subtraction, left to right. Well, it's important that you understand that a radical corresponds to an exponent. And I'm going to show you that here at the end of the lesson today. Radicals correspond to exponents. So if you were to perform the order of operations, you would have to include exponents and or radicals. Then multiplication, division, left to right, then addition and subtraction, left to right. So we need to deal with the radical first. Still got the 5, still have the minus sign. All right, we need to find out what number times itself 3 times equals 1,000. Well, 10 times 10 is 100, times 10 is 1,000. So the cube root of 1,000 is 10. And now we have this simplistic problem. 5 positives and 10 negatives leaves us an ultimate solution of negative 5. Follow the order of operations. That's it. All right, so what if you had, how about this? How about a 4th root? Oh no, I'm shaking in my boots, right? No, it's no big deal. It's no big deal. What number times itself 4 times equals the radicand? I mean, that's the situation. That's what we're dealing with. This one really has 2 portions to it. Let's deal with the number 16 first. Because the 16 is multiplied times the p to the 4th, we can deal with it separately. 16 is a 2 times 8, and 8 is a 2 times 4, and a 4 is a 2 times 2. Now remember the question of the cube root. What number times itself 4 times is a 2 times 2 times 2 times 2? I sound like Cary Grant there. All right, and the answer is 2. All right, it is 2. And then look at the second situation here. I'm going to do this one in black. Here we have the situation again where the exponent matches the index. And remember, the root is always the base. So we ended up with 2p. So the 4th root of 16p to the 4th is simply 2p. All right, not in a pod. All right, number 3. Number 3. So if we're going to find each root, really what we need to do is to factor the radicand. Factor the radicand. And that's really the key. And you can see that's what I did up above, right? Right here, what did I do? I factored the numbers of the radicand. That's what we need to do. Now, we're going to talk about this a whole lot more tomorrow when we get into simplifying radicals. But that's what's going on. All right, so a lot of people already know that the square root of 36 is 6. But again, why? Because a 36 is a 6 times 6, right? And therefore, the answer is 6. Cube root of 125, you may not be sure about that. All right, 125, right? That is a 5 times 25. And what is a 25? A 5 times 5. Hence, the cube root of 5 times 5 times 5, which, by the way, is a 5 cubed, is 5, right? So 81, we're going to do the same thing. Now let's go 9 times 9. So this 9 is a 3 times 3. And the other 9 is a 3 times 3. And now we have 3 to the 4th power. And what's the 4th root of 3 to the 4th power? It is 3. All right, it's the idea. It's what we're dealing with. And that's the situation. Okay? All right, I have to get rid of my screen here so I can move higher. All right, look at number 4. Even roots. Even roots. All right, what do we mean even root? What do you mean even roots? All right, we're talking about an index that's even. So 2, 4, 6, 8, 10, 12, 14, etc. An even index is what we consider to be an even root. So here's the reality. Even roots of negative radicands. Even roots of negative radicands result in a solution that is not, underlining not, a real number. So we say not real, or we could say undefined. Here's the reality. When you get to Algebra 2, we're going to teach you about imaginary numbers. Hey, they're not real, are they? They're not. They're imaginary numbers, and we'll be able to figure out even roots of negative radicands. But for right now, we're just saying undefined. Because here's the situation. Let's look at the first one, and then we'll do the others quickly. Hey, remember, negative 16. What number times itself 2 times is negative 16? And you might say negative 4. Well, not true. Negative 4 times a negative 4 is a positive 16, and that does not equal our radicand of negative 16. You might say, okay, negative 4 times positive 4. Oh, no, 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 no. That's not the number times itself, right? It's got to be the number times itself, a negative 4 times a negative 4, or a positive 4 times a positive 4. In both cases, you get positive 16, not negative 16. So in reality, we don't do anything to these. We say not real, not real. Second one, oh, the 12th root of negative x. I don't care what's in there. It's an even root of a negative radicand, and guess what? We say not real, not real. Now, C's different. It's a horse of a different color. This is an odd root. Okay, you know what? You can take the odd root of a negative radicand. Negative 8 is a negative 2 times a negative 2 times a negative 2. Doesn't that equal negative 8? Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is a negative 8. Oh, yeah. You know what? Negative 2 times itself 3 times equals that radicand. We have a solution there. And you will for any odd root, cube root, 5th root, 7th root, 9th root, because you can end up odd with an odd solution. Okay? All right. Sometimes they want you to estimate. You know, in our day and age, to be honest with you, we have calculators everywhere. Your cell phone has a calculator. Aging myself there when I call it a cell phone. Your phone has a calculator. Calculators are everywhere. Your car probably has a calculator. So this isn't as much of a big deal, but it is kind of the aspect of knowing where something lies. All right, so what do you do? To estimate the root to the nearest integer, find the root of the perfect square or cube less than and or the perfect square or cube greater than. And you know what? Instead of going to the nearest integer, let's go to the nearest tenth just to make life a little bit more interesting. Nearest integer is easy. I'll show you that, but then we're going to also go to the nearest tenth. All right, so let's take square root of 125. So I'm trying to think of what perfect square is just lower than 125, and it's the square root of 121, because the square root of 121 is 11. So therefore, the bigger one has to be what gives me a square root of 12, right? And 12 comes from a radicand of 144. Okay, so I have 121 and 144. So hopefully you would agree, if I go in the nearest integer, I'm going to say 11, because 125 is a whole lot closer to 121 than it is to 144. Now, when I was writing my notes for this lesson, I just guesstimated, and I said, I wonder what that, I'm going to guess. If I were to guess to one decimal place, I'd guess about 11.2, and I hit it right on. I punched it in my calculator after that, square root of 125, and it was 11.2. Okay? To the nearest integer 11, if I were going to one decimal place, my guess would have been 11.2. You may have guessed 11.1. You may have guessed 11.3. You know what? It's an estimate. So it's okay. Should be in the vicinity, though. You're not going to guess 11.5, I hope. Then you'd be too far away. All right, let's do the cube root. Cube root. All right, it's a little bit more difficult for students to think of, because you got to think of the perfect cube root below a cube root of 211. And that's actually the cube root of 125. Because a 5 times 5 times 5 is 125. So therefore, on the other side has to be a cube root of what produces a 6. And believe it or not, 6 times 6 is 36 times 6 is 216. So we got to be between 125 to 16. Now, if I were going nearest integer, I'd say 6, right? I'd say 6, because 211 is a whole lot closer to 216 than it is to 125. Now, when I guessed on this to the nearest tenth, I said 5.9. However, when I punched it in, if I rounded off, it would have been 6.0. So, because it was like 5.95. All right. But estimating. All right. Again, not a big deal with that today, but we need to get this last part, and this last part's really important. And as you begin to understand the switching between radical form and exponent form, so then you begin to understand what's happening with radicals. Remember earlier I said the order of operations evaluate all exponents, and I said radicals are just like exponents. Well, here's why. Here's why. Here's our rule. If you look right here, right, we've got the bth root of x to the a. Well, here's the reality. We can convert this to exponent form. Take the base of the radicand, the x, and now we're going to have a fraction for an exponent. The exponent of the radicand is the numerator of the fraction, and the index is the denominator of the fraction. So use your color there. So x to the a over b is the b root of x to the a. Wow. That's exactly it. Now, while we're at it here, I also want you to be aware of this, that this bth root of x to the a is also the same as the b root of x, that whole quantity, to the a power. Say, how is that the case? Okay, let me do our rule for just this part. The x has a 1 exponent, not shown. So if I use the rule, it would be x to its exponent over the index of b. But remember, it is this whole quantity to the a power. You remember your exponent rules? X to the a all to the b power equals x to the a times b. So what do we end up doing? We end up multiplying this a times 1 over b, and what do you get? X to the a over b. All right, pretty cool. I'll bring that up a couple more times to help solidify that in your mind. But here's the key. You've got to learn this. You've got to memorize it. You've got to understand that pattern to be able to switch between radical form and exponent form. And this is highly testable. Highly testable. You are definitely going to see this on your next quiz. You are definitely going to see this on the test. No doubt about it. Highly, highly, highly testable. Okay? So focus in here as we look at changing. Okay, so I'm using color here in the beginning, make life easy. So if you're able to follow the pattern, if we're going to change it from radical form to exponent form, we take the base of the radicand, we take the radicand's exponent, and we divide it by the index. Those are exactly the same. The fourth root of 2 to the fifth is exactly the same as 2 to the 5/4 power. So here's an interesting thought. Look at the next one. Now, if you want, pause the video, see if you can figure out how to put it into exponent form. And this is a key one. This is an important one. All right? Well, let me add in what's not shown. What's the exponent of 7? I'm going to write in red a 1, right? Because it is a 1, it's just not shown. And what's the index of a square root? Well, it's a 2, and it's not shown. So if we go ahead and write 7, take the 7's exponent, and put it over the index, we have 7 to the 1/2 power. What's the square root of 7? 7 to the 1/2 power. All right, now stay with me. Stay with me. Don't write this in your notes. I just want you to think. I'm going to put it on the screen so you can visualize it here, and I'm going to put it right in this box right here, okay? What is, let's go this way. What is 16 to the 1/2 power? Answer, 16 to the 1/2 power. All right, if you're thinking 4, you're thinking right. What is 81 to the 1/2 power? If you're thinking 9, you're thinking right. See, what in the world are you doing? Well, remember, 16 to the 1/2 power is the square root of 16. Answer 4. 81 to the 1/2 power is the square root of 81. Anything to the 1/2 power is a square root. Square root. All right, that's a key concept. I'll try to keep bringing that up and reminding you of that. Well, look at here. Now we have a cube root. Let's do the exact same thing. What's the exponent of that 5? It's a 1. So changing into exponent form, we get the 5. Its exponent is the numerator over the index of 3. So 5 to the 1/3 power means the cube root of 5. Hey, what's the answer of 8 to the 1/3 power? 8 to the 1/3 power? Same thing as the cube root of 8. The answer is 2. What's 27 to the 1/3 power? Same thing as the cube root of 27. Answer, 3. So a half power is a square root. A third power is a cube root. That's a key concept. Again, you need to be able to convert. All right, here's a few more. Number 4 is a little different because in reality, we can factor this 9 into a 3 times 3. So really our 9 becomes, I'll use my color here, a 3 squared. So now when we write it in exponent form, we get 3 to the 2/3, which is a more simplistic form than 9 to the 1/3. 9 to the 1/3 is true, but it's not as simplified as 3 to the 2/3, and we want to be as simplified as possible, right? We want to be as simplified as possible. Okay, man, I'm running out of time, and that's tough, but oh well. All right, so this next one, we've got, let me get rid of that, use my red here. So this next one, we've got a couple things going on in the Radicand. You know what? Don't let that throw you. Don't let this throw you. You have to deal with each one. They're all multiplied together, and that's the key. And therefore, you deal with each one separately. 2, its exponent over the index. So that's 2 to the 1/5. Does that make sense? Okay, times. You could put a raised dot, but you don't need one. If we write two things together with nothing in between, it's multiplication. X. What's its exponent? 2. What's the index? 5. And then finally y, and what's its exponent? 3 over the index of 5, right? And so 2 to the 1/5, excuse me, sorry about that, 2 to the 1/5, x to the 2/5, and y to the 3/5. Okay, here's that other form. But look, here's the reality. Take the radicand, it's the base, there's its exponent, which is the numerator, and there's the denominator. That's 5 to the 4/7. That's how those work, and that's how those go. All right, you're going to have to do that tonight. And again, there's a key concept. You're going to see it on all of your quizzes and your tests. All right, how about going the other way? Now we're going to go backwards. So if you look up at the rule, now we got to go from this form back to radical form. We're going backwards. That's okay. Not hard to do. We're just going the other direction. We can do that. All right, so 7 to the 1/2. We're going radical form, so I'm going to draw a radical symbol. All right, I'm going to put the base inside the radicand. Now, because it's a 1, I don't show that 1, right? Though it is 7 to the 1 power, and because it's a square root, I don't show an index of 2, although the index is 2, right? And we get the square root of 7. All right, Number 2 is actually a little easier because we're going to show both the exponent and the index. So we're going to have 11 cubed as the radicand, right? And what's the index? It is a 5. Now I will tell you this. We're supposed to simplify numbers. So this is going to end up the fifth root of 11 times 11 times 11. And that is 1,331. You have a cube root button on your calculator. We'll deal with that when we have a little bit more time. All right? Cube root. So you end up with the fifth root of 1,331. All right, here's a double example, but that's okay. Remember, here's our index, right? It's a 4. So we're going to write our radical sign. We're going to put our 4 in for the index. Our first one is 3 to the first power, so we can just write 3. And then what do we have? X, and what's its exponent? Cubed. So we have the fourth root of 3x cubed. The fourth root of 3x cubed. All right, what do you got to do on a problem like this? Well, look, these denominators don't match. That's a problem. And they need to match. So what are we going to do? Get a common denominator so that they'll have the same index. We don't want to make 3 different radicals. We want one radical. All right, common denominator. We can do that. Let's multiply this one by 2 over 2 to get a 6 on the bottom. Let's multiply this one by 3 over 3 to get a 6 on the bottom. Where do we end up with? 2 to the 4 sixths, z to the 3 sixths, and we have y to the 5 sixths. Putting that in radical form. There's my radical sign. What's the index? 6. 2 to the 4th, z cubed, y to the 5th, and I got to simplify, right? I got to change that back into a number. So this is 6, and then 16, which is z at 2 to the 4th, z cubed, y to the 5th. And that's the solution. That's it. All right, I'm about out of time. So number 5, you can do the exact same thing. Get a common denominator, and then go ahead and put that into proper form. Common denominator, and put that into proper form. And then a couple of situations here on the bottom, and hopefully I will come back to them in just a moment.